A dragon curve is any member of a family of self-similar fractal curves, which can be approximated by recursive methods such as Lindenmayer systems. Hayway dragon. The Hayway dragon was first investigated by NASA physicists John Hayway, Bruce Banks, and William Harter. It was described by Martin Gardner in his Scientific American column Mathematical Games in 1967. Many of its properties were first published by Chandler Davis and Donald Knuth. It appeared on the section title pages of the Michael Crichton novel Jurassic Park. Construction. It can be written as a Lindenmayer system with angle 90 degrees. Initial string fx. String rewriting rules xx plus eve plus y minus fx minus y. That can be described this way. Starting from a base segment. Replace each segment by two segments with a right angle and with a rotation of 45 degrees alternatively to the right and to the left. The Hayway dragon is also the limit set of the following iterated function system in the complex plane, with the initial set of points, using pairs of real numbers instead. This is the same as the two functions consisting of this representation is more commonly used in software such as Apophysis. Unfolding the dragon. Tracing an iteration of the Hayway dragon curve from one end to the other, one encounters a series of 90-degree turns, some to the right and some to the left. For the first few iterations, the sequence of right and left turns is as follows. First iteration, R second iteration, RRL third iteration, RRL fourth iteration, RRL. This suggests the following pattern. Each iteration is formed by taking the previous iteration, adding an R at the end, and then taking the original iteration again, flipping it retrograde, swapping each letter and adding the result after the R. This pattern in turn suggests the following method of creating models of iterations of the Hayway dragon curve by folding a strip of paper. Take a strip of paper and fold it in half to the right. Fold it in half again to the right. If the strip was opened out now, unbending each fold to become a 90-degree turn, the turn sequence would be RRLIE. The second iteration of the Hayway dragon. Fold the strip in half again to the right, and the turn sequence of the unfolded strip is now RRL. The third iteration of the Hayway dragon. Continuing folding the strip in half to the right to create further iterations of the Hayway dragon. This pattern also gives a method for determining the direction of the nth turn in the turn sequence of a Hayway dragon iteration. First, express n in the form k2 meters where k is an odd number. The direction of the nth turn is determined by k mod 4, i.e. the remainder left when k is divided by 4. If k mod 4 is 1 then the nth turn is r. If k mod 4 is 3 then the nth turn is l. For example, to determine the direction of turn 76,376. 76,376 equals 9,547 by 8. 9,547 equals 2,386 by 4 plus 3, so 9,547 mod 4 equals 3, so turn 76,376 is L. There is a simple one-line non-recursive method of implementing the above k mod 4 method of finding the turn direction in code. Treating turn n as a binary number, calculate the following Boolean value. Bool turn equals less than 1, and n equals 0, n and minus n leaves only one bit as of 1, the rightmost one, in the binary expansion of n. Less than 1 shifts that bit to the left one position, and n leaves either that single bit, or a 0. So, bool turn equals less than 1, and n equals 0 is true if the nth turn is L, and is false if the nth turn is R. Gray code method. Another way of handling this is a reduction for the above algorithm. Using gray code, starting from 0, determine the change to the next value. If the change is a 1, turn left, and if it is 0, turn right. given a binary input, b, the corresponding gray code, g, is given by g equals b XOR, using g and g-1, turn equals, and g-1, g equals b caret, this gets gray code from binary. T equals and G1, if T is equal to 0 turn clockwise else turn counterclockwise. Dimensions. In spite of its strange aspect, the Hayway dragon curve has simple dimensions. Note that the dimensions 1 and 1.5 are limits and not actual values. Its surface is also quite simple. If the initial segment equals 1, then its surface equals. This result comes from its paving properties. The curve never crosses itself. Many self-similarities can be seen in the Hayway dragon curve. The most obvious is the repetition of the same pattern tilted by 45 degrees and with a reduction ratio of. Its fractal dimension can be calculated. That makes it a space-filling curve. Its boundary has an infinite length, since it increases by a similar factor every iteration. The fractal dimension of its boundary has been approximated numerically by Chang and Zhang. In fact, it can be found analytically. This is the root of the equation. Tiling the dragon curve can tile the plane in many ways. First element with 4 curves. Second element with 4 curves. Third element with 4 curves. The dragon curve can tile itself. First element with 2 curves. Second element with 2 curves. Third element with 2 curves. Example of plane tiling. Example of plane tiling. Example of plane tiling. Dragon curves of increasing sizes form an infinite spiral. 4 of these spirals tile the plane. Twin dragon. The twin dragon can be constructed by placing 2 Hayway dragon curves back to back. It is also the limit set of the following iterated function system, where the initial shape is defined by the following set. It can be also written as a Lindenmayer system. It only needs adding another section in initial string. Angle 90 degrees. Initial string fx plus. String rewriting rules xx plus ef y fx minus y. Terdragon. The terdragon can be written as a Lindenmayer system. Angle 120 degrees. Initial string f. String rewriting rules ff plus f minus f. It is the limit set of the following iterated function system. Eliacute Vy dragon. The Eliacute Vyc curve is sometimes known as the Eliacute Vy dragon. Occurrences of the dragon curve in solution sets. Having obtained the set of solutions to a differential equation, any linear combination of the solutions will, because of the superposition principle, also obey the original equation. In other words, new solutions are obtained by applying a function to the set of existing solutions. This is similar to how an iterated function system produces new points in a set, though not all ifs are linear functions. In a conceptually similar vein, a set of Littlewood polynomials can be arrived at by such iterated applications of a set of functions. A Littlewood polynomial is a polynomial where all, for some w less than 1 we define the following functions. Starting at z equals 0 we can generate all Littlewood polynomials of degree d using these functions iteratively d plus 1 times. For instance, it can be seen that for w equals 2, the above pair of functions is equivalent to the ifs formulation of the Hayway dragon. That is, the Hayway dragon, iterated to a certain iteration, describe the set of all Littlewood polynomials up to a certain degree, evaluated at the point w equals 2. Indeed, when plotting a sufficiently high number of roots of the Littlewood polynomials, structures similar to the dragon curve appear at points close to these coordinates.